Do you know what? I'm going to have a quick talk about these questions here, and then on the next slides, we're going to give the answers. I just want to give a bit of an overview. In fact, maybe it's a good opportunity to, because if I'm going to export this as a video, for you to have something on registers. So what are the registers allowing us to facilitate? That's exactly, so the registers allow us to do the fetch, decode, execute cycle. So we've got these four registers which help us facilitate the fetch, decode, execute cycle. Then we have components of the CPU that facilitate it, like the CU standing for control unit and the AOU standing for the arithmetic logic unit. Beautiful. And here we're going to start with which register first. Yeah, we start with the PC, which is the program counter, and the program counter has the address of the next instruction to be used. There you go. So in here it's 000001, and that then passes the value from the program counter down to the memory address register, so that inherits the same value, 000001. And then what happens? The PC increments by 1. So that is one of the two things you can say. The program counter, here's the three things you can say about the program counter. 1, it holds the address of the next instruction. 2, it passes the contents of the program counter to the memory address register. And 3, it increments. Now, I've probably made a boo-boo there by writing 2. I should probably, because it's in binary, I should have said 000010, but just ignore it for the second. Oh, geez. Here, now we're at the memory address register. This is not the next instruction to be read. This is the address of it. So this value needs to go off into memory and find it, and then the contents of it needs to be put down into the memory data register. And then over here we have the contents of that. Now in this context it's an instruction. If you got the value from there and put it there, we split into two sections. What are the two sections of an instruction? As I was saying, as we were saying, there's two sections to an instruction. The red bit indicating the opcode and the blue bit being the operand. The opcode being the function you want to do. This could be to add, to subtract, to take away, etc. And then we've got this bit here, which is the operand, which is the value that you want to apply the opcode to. The contents of the MDR is then passed onto the CIR. So we'll have the same values down here. And then we've got to figure out what on earth we need to do with it. So it's a great question. So it's still split into the two sections at the moment, the operand and the opcode. And it needs to be, because what was the cycle we're going through? Fantastic. So this is the fetch, decode, execute cycle. So far, we've been fetching. At this point, we're now in the next phase, the decode phase. So we need to know what on earth that opcode is. Now, 011 doesn't mean anything to us, but if we send it to the control unit, which is what we'll do, it can figure out what we're supposed to do. Maybe it's to add, maybe it's to subtract, etc. And then that... Sis? Yeah, that's true. But it's still decoding. I suppose the control unit will still be in charge of however you're going to achieve that. It might take multiple process cycles. This bit here, though, there is a depending bit here, the operand. Now, that could be the value 3. If it's the value 3, it means it's what type of addressing are we using. So if it's the value 3, it means it's using what's called immediate addressing. And immediate addressing means that the value you use straight away has some great advantages. Number 1, it's a lot faster because you don't have to fetch whatever that is. Number 2, though, here's another issue, though it's got with it, is that can you use it as a variable? Well, no, because you can't change it. It's hard coded now, that value. You might use it for things like constants or maybe the value of pi if you're storing it, or the value of gravity because you're not intending to change it. What happens if I said that number there was the address 3 where I could find it? So that's an address number 3 and I can find the value there. What am I using then? What type of addressing? Yeah, so that would be a direct addressing. Now, the way that would work is that 3 would be sent to the memory address register. Then the memory address register would get the value here and drop it into the MDR ready for me to use. The reason why you're doing that is currently the biggest number I can make in this 6-bit processor, only 3 bits can use with a value. So the largest I can make is 7, and the smallest is 0. So I only can have 8 values. The reason why you use direct is suddenly I can open up a lot more values. I can use all of these. So I can use all 6 bits, which would take me to 64 different values. So it gives that big advantage. Now, the other one will be indirect. And if you remember, what that would mean is that you go back to memory, find the address. So it can be any one of 64 different addresses, and then get the value back again. The ALU in the end is where what happens? Which part of the cycle? Yeah, maths, logics, addition. Essentially, this is where the instruction would eventually be executed. So let's say we're using direct addressing. What would happen is 5 would get put into the MAR. It would use that with the address bus to get the contents into the MDR, and then the value would be taken to the accumulator inside the ALU to be used. So that is just a bit of an overview. So let's return to the actual question. So the question was, describe the role of the control unit in the processor. So what I would say is the control unit helps manage this fetch, decode, execute cycle, number 1 point. Number 2 point, it passed it here. What was happening at this point when it was passing it down? It helps decode it. So over here, I've got the actual answers here for us to look at. I'm not sure, is that easy to see or is it a bit too small? Can you see that? How about that? Better? Okay, cool. So you see here, number 1 mark decodes the instructions. There you go. Number 2, if I'm going to be frank, I think a lot of people gave this a good go, but weren't quite clear enough about what they were trying to say. So it says here, it sends control signals to coordinate movements of data through the processor, execute the instructions. Now, this is what I'm saying. It helps, do you see it? Except manages or coordinates the FDE cycle. But you have to be clear about how you're going to say, because it says here, some candidates answer this question, how descriptions lack detail. So I think you have to be aware about what keywords you're using. So when you're saying it sends control signals, what bus is it using to send those signals? The control bus. And again, literally saying the control bus gets you the second mark out of the 3. So I suppose if I'm describing the control unit, I'd say it manages the fetch, decode, execute cycle. It achieves this by sending synchronized signals using the control bus to manage that fetch, decode, execute cycle. And did I say it also decodes the instructions? I mean, that's the point you're trying to make for that one there. And I think a lot of people were saying the right things, but they're just a little bit confused about how you're doing it. So I'll leave this up so you have this. The other, talking about the details of the program counter and the memory address register and the memory data register. Let me give you one big tip. If you can just talk about it chronologically, i.e. the program counter, it does some stuff which we've already discussed, but you say that it passes the contents onto the memory address register, that's a mark. If you say that, yeah, exactly, right, and you probably got the marks for that. If you said that the contents of the memory address register, it goes to the memory gets the contents of that and puts it to the memory data register. That gets you a mark. So I'm gonna increase the size of these ones here so we can have a quick look through. So the top one is the program counter. It's saying it's needed to store the address of the next instruction. What is one of the ways you can easily lose the mark there is by saying something along the lines of it holds the next instruction, which we know it doesn't. It holds the address. The value is then sent to the MAR. Like, this is what I'm saying. That's the easy mark. Do not be losing that mark. And after sending it, it increments. I think we just talked about all that. The MAR contains the address of the instruction. You get the mark again for saying that's what it's got. And saying you got it from the PC. You get the 2 marks for saying just the chronology here. That's some easy marks. And you can say it contains the address of the data if it's sent from the CIR. This bit here, what does this mean? Contains the address of the data sent from the CIR. What's it talking about there? You're right. So this is what we were just discussing. This is when you're using direct or potentially indirect addressing, and the CIR is having to send the operand because it's the address of the data. All right, let's see, 2 marks. And then finally, we're going to look at this last one here, which is the CIR. Finally here, we've got the current instruction register. MDR. My apologies, you're quite right. Thank you for the correction, Mox. The MDR. So this is saying now, what's the difference? Well, it's saying it contains the instruction which has been accessed from memory. So it's saying it's gone into memory, it's retrieved the contents from the memory and put it there. That's if it was sent from the MAR directly from the PC, or it was from the CIR and it's direct addressing, it could be the data. And then it's saying it acts as a reference. Oh, and a lot of people got this, that it acts as a buffer. A lot of people got that mark there. Yeah. It basically acts as if you think about it, what's being held in the MDR and what's being held in the CIR can actually be the same a lot of the time. So it's acting as a buffer, so there are any changes made, it's temporarily holding it. Yeah? Yeah. Cool. Right. And then we've got the floating point question. I reckon we do this. We do the floating point question, and then you guys... Okay. So on the left here, pay attention to the points it's making at the top. They are absolutely crucial about the 7 bits for the mantissa and 5 bits for the exponent. I'll zoom in a second, but obviously that concept is very important. So the first 7 bits are the mantissa bits, and the second is for the exponent. And if you get that wrong, obviously you're going to be walking uphill. So for these questions, that means that, in fact, okay, guys, this is the mantissa, exponent, mantissa, and exponent. Reviewing that, it's saying that which of them is normalized. Well, you can see here, for it to be normalized and it's a negative number, it will be 1.0 if it's negative, right? And if it's positive, it's 0.1 something if it's positive. Well, if we look here, 1.0, so that indicates that it is normalized. There you go, and negative, quite right. But 1.1, can you start with 1.1? No. Just quickly, the way you'd fix this is that you get this and you'd have to move it up by 1. And remember, we get into the issue as whether that takes 1 off the exponent or adds 1 to the exponent. And remember, my tip for that was always, if you're not too sure, 13.7 times 10 to the 4. Oh, it's the other way around, you see here. If I wanted to move it, but make it that way, I've made the mantissa larger. If the mantissa becomes larger, what do I have to do with the exponent? Yeah, so that would be taking 1 off. So here, if you're moving 1 to the right by making it larger, you'd have to take 1 off here. Okay, and then the other one was this one. It's not normalized, write it as normalized. Oh, I can do that super quick, can't we? So the first 7 was going to be mantissa. What we need to do then is write out the mantissa. In this case, 001101, and the exponent, so that'd be like times 2. You don't have to write it out like this, but I'm doing it just because you can see what it is. So what we can see here is that this is not normalized, and it's going to be a positive number. The dot is here, or the point is there, and we need to move it left or right. Sure we do. We have to move it once and twice, which will make it 0, 1, 1, 0, 1. Yes. There you go. I have to pad, so I've only got 5. 1. So I've made it. If I've made that larger, I made the exponent exactly right. So there you go. So that's 1. That's why I try and do that tip. Write it out in denary. So you're like, oh, it's obvious now. But we're not equipped to think binary. So. Is 3. So yeah, you did. So yeah, this is why I'm saying it quite often. It's a very easy place to go wrong, and unfortunately, if you do so, you've really sucked yourself a bit there. So yes, 5. Yeah, it happens, but what we need to do is make sure we've learned the lesson. As you say, 5 becomes 3 here, and then that is your answer. Sweet. All right, here we go. So this is the question that obviously we love. It's beautiful in every single way. Let's talk about how to get some of the easy marks here. The easy marks is actually, you put them all, if you want to add up numbers, I've said this before, if you use it under a common denominator, it'll work. But let's just forget that, okay? Because the mark scheme says, put it into fixed point. And obviously fixed point is a common denominator. But let's just say, if we want to add up floating point numbers, the very first thing we do is put it into fixed point. Because if you put it into fixed point, you're going to get marks just for doing that. So let's do that quickly. Yeah, if that gets down to 0, so that's put into fixed point. So it goes down by 2. That's getting smaller. This one must become bigger. So essentially what we're saying is that this is going to go once, twice, there. So in fact, maybe I can make it, there you go. So we need to turn that into 1, 0, dot 1, 0, 0. And then we'll do that with the other ones. I'll pause. So that puts it into fixed point. You get actually a mark for that one, and for that one, and for that one. The places where it can go wrong, is that sometimes, in fact, I don't think it is the case with this one. I was going to say, if I start labeling what these things actually are, we've got 1, 2. On this way, we've got half, a quarter, an eighth, and a 16. What am I going to write here? Yeah, but well, you could easily write 4, and that would be wrong in this context, because this number, that would make that 4 and a quarter, yes? And actually, yeah, well, exactly, we know it must be negative, and actually in this context, it's negative 4. And if you want to actually do it, I'll show you what it is in Denary. We can actually go through it, because you can check your answer. You can say that's 2 and a half, so that's 2, you can say it's 2.5. This last one's the way to go trickier. So it's negative 4 plus a quarter. Yeah, exactly. Okay, let me be clear. I'm not saying just add it in Denary and then write the answer. Okay, so you can say it's, okay, what I'm saying is that when you do these kind of questions, you could check, couldn't you? You could check yourself at the end to see if you got it saying it matches up. Yeah, and that would be my tip, because if you've checked it to see if it matches up, then you can see, oh, I got the right answer, and you can, in a sense, you're like almost marking yourself. Also, something I point out here, is it going to be, so 4, take away 3.75, is the answer going to be positive or negative? Positive. So is it going to have a 1 at the end? So if you got a 1 at the end, guess what? There you go. Yeah. That's why I'm gonna do it right now, because I think that now I can totally see, because normally when we add it up, it means let me just do it and I'll discuss it as we go along. So I'm gonna add it up all together. Like if I'm in your shoes most of the time, I'll be adding it one to each other, because sometimes you can have 3 ones and you get confused. But let's do it here. Actually, here we've never got more than 2 ones anyway. So 0, 0, 1, 0 carry the 1, 0 carry the 1, 0 carry the 1, and then 0. And then you're saying there's a 1 over here, isn't it? Yes, we refer to that as an overflow error, and we say the way to solve that is by adding extra bits. Now, I want you to consider something, though. If it has a 1 at the end, can it ever be a positive number? So that 1 there is actually being pushed off to allow you to go from a negative number up into a positive number. Okay. And we said, by the way, FYI, we said that the answer in the end was going to be a quarter, and we can see that the answer is a quarter there. Do we have to put it back into floating point? Okay. Well, that's no piece of cake. Come on. How do we... Well, in this context, we just got to go back by 1, don't we? Yeah? So we can say that is 0. Is it 6-bit mantissa? Yeah. 1, 2, 3, 4. So that's 6. The mantissa, by going to the right, have we made it larger or smaller? There you go. So the exponent currently is 0, so we have to go 1 off 0. Yes? And and we have to say it's yes, exactly. 1, 2, 4, -8. To get to -1, which is where we need to be, we have to go 1, -8, and then add the 4, -4, add the 2, -2, add the 1, -1. And there we are. There you go. Done. Son. Guys. So yeah, or 1 if it's on its own. So we're in a Kano map always trying to successfully draw the largest blocks we can make. So obviously what we could do is draw a 2 and a 2 and a 2 and a 2, but that would be stupid. And why would it be stupid? Because 4s would be larger and therefore would be more efficient. Bear in mind, you can also wrap is there any opportunity to wrap on this question here, as in wrap around? There is no opportunity to wrap, and therefore we won't do it, but it's worth bearing in mind when we do it. So I'm going to try and draw the two squares, hopefully successfully. So we've drawn the two blocks. So this, oh, and also maybe it's worth saying, again, what is the big picture? What we're trying to achieve with a Carnot map? Yeah, simplifying a logical circuit. So essentially you can achieve the same goal in a with a logical circuit by using many more gates or less gates. And if we can use less gates, that's going to make a much more efficient computer. In fact, it's not that dissimilar because we've just done compilation. Do you remember the steps of compilation? Okay, so now that we have these circles drawn here, these blocks rather drawn here, we want to write down what is the Boolean expression for these things. And if you look at it, we're looking at here that we're looking at what stays the same and what changes. So on this way, we can see, does C stay the same? So yeah, not C is consistent. So not C. And what is the other element? So does D stay consistent? Does not. And not A stands consistent as well. This is represented by this expression here. To link together the different expressions, what symbol are we going to use? There you go. And I've done the same I've done before, but like that should all be on the same level, really. So that's, yeah. Yes. What is the other two elements? Yes, Itichamp, good job. And it's come back to life, hopefully. Man, I've literally got a phone call now. This is just... I've got a phone call from school, I think. 1 second. Back to recording. So on here, we want to then make the expression. I want to make the expression for this element here. And again, we need to look to see what stays the same or what changes. So on this top bit, what stays the same? So the expression must be A, and then we link it with an and on this side, we're saying C, exactly, C. Right. I'll be honest, a lot of people did this bit successfully, but weren't able to do the logic circuit correctly. We'll record this. So in here, yeah, we need to do the NOT gates will be first, and then we need to do the two AND gates, and then going into an OR gate. So we're doing that. I'll do my beautiful drawing skills. In fact, let's zoom in. Boom. There we go. So over here, we've got that top one, the two NOTs going into an AND. Underneath it, I'll do another AND. Now, let me show you one of the places where people really went awry. Here's one of the places where people had a big issue. So as I was saying, there's an A and a C going in here. And here's one of the issues that people had, is they did an additional A and a C down here, giving the impression that there's two separate A and C inputs. But really, they all need to be coming to the same place. And let me show you how you fix that quickly, is that you can just say that C is going in here. You only do like a little bobble there. And then the A needs to jump, come over, and there it is there. Yeah, and then it goes into an OR. Oh, gee, that's ugly. I mean, really, even by my standards, that's poor. Like, I know. Even when I take my time, it's pretty awful. Boom. Indeed. Okay. Yeah, I know. Shh. Anyway.